Welcome back to another deep dive. We're so incredibly glad you're here with us today.
Yeah, absolutely.
Whether you are prepping for a big meeting or maybe trying to catch up on a new field, or you are just one of those insanely curious people who loves to learn, you are in the exact right place.
You really are.
You are the learner, and this show is entirely custom tailored for you. Today, our mission is to unpack the basics of experimentation. We're going to look at the fundamental building blocks of how scientific truth is actually constructed,
Mhm.
and just as importantly, how you can properly evaluate it.
And if you're wondering why you should care about the dry mechanics of scientific experiments, just think about the world we live in right now.
Right.
We are absolutely drowning in data. Every single day you see news articles, social media posts, presentations at work claiming that a new study has proven some incredible claim.
Oh, I mean, constantly.
Exactly. So understanding the concepts we're discussing today is really the ultimate shortcut to being a truly well-informed person. It gives you a critical toolkit to evaluate literally any statistic or piece of research that gets thrown your way. You won't just be taking claims at face value anymore. You'll actually be able to see the scaffolding behind them.
You essentially become a data detective, which is a pretty great superpower to have. Okay, let's unpack this, starting with the absolute basics. Every experiment starts with the thing you are actively tinkering with, right?
Right, the thing the researcher changes on purpose just to see what happens.
Yeah, and in science, we call this the independent variable, or the IV. It's the antecedent condition that an experimenter intentionally manipulates. And a true experiment requires at least two levels or, values of this independent variable.
Which makes perfect sense when you think about it. If you don't have at least two levels, you have nothing to compare.
Exactly.
Let's say you want to know if caffeine affects memory. You can't just give everyone a cup of coffee and test their memory.
Because what are you comparing it to?
Right, you need a level with caffeine and a level without it. Or maybe a low-dose level and a high-dose level. You have to establish a contrast. Now, the counterpart to that independent variable is the dependent variable, or the DV. This is your outcome measure.
So the independent variable is the cause, and the dependent variable is the effect.
Exactly. The dependent variable is what the experimenter uses to assess the change in behavior that was produced by that initial manipulation. The crucial concept here is the cause and effect relationship. If the experiment is done right, the dependent variable depends entirely on the value of the independent variable.
Simple enough in theory, right? You change one thing, you measure the result. But here is where we start to see how easily things can go completely off the rails in practice. Let's talk about confounding.
Oh, yes, the dreaded confounding variable.
A confounded experiment is basically a ruined experiment. It happens when the value of an extraneous variable systematically changes right along with your independent variable.
And this is where that critical toolkit we talked about comes in handy for you as a reader. Imagine you are running an experiment and you decide to test all of your experimental subjects in the morning,
Okay.
but you test all of your control subjects at night.
Oh, I see where this is going.
Yeah,
You might spend months on this study, but if you see a difference in the outcome, you have absolutely no idea why it happened.
precisely. Was the change in the dependent variable because of the independent variable you were trying to test? Or was it simply because people are generally more alert in the morning than they are at night? Time of day just became a confounding variable.
Wow.
Because it systematically changed alongside your independent variable, your final results are rendered totally ambiguous.
It really highlights how incredibly precise you have to be before you even begin. You can't leave anything to chance, which leads us perfectly into how researchers actually lock down their variables so everyone is on the same page.
They use operational definitions.
Right. You can't just casually say you're testing something abstract like happiness or memory.
Yeah.
You have to define it in terms of observable operations, procedures, and measurements.
And there are two distinct types of operational definitions you need to establish. First, you have experimental operational definitions. This specifies the exact step-by-step procedure for creating the values of the independent variable.
So what exactly did you do to manipulate this situation?
Exactly. If you're testing caffeine, your experimental operational definition isn't just we gave them coffee, it's we administered 200 milligrams of caffeine in 8 ounces of water at 9:00 a.m.
You have to spell it out so clearly that anyone else could copy you.
Right. And second, you have measured operational definitions. This specifies the exact procedure for measuring the dependent variable. How exactly are you scoring the outcome? Without both the experimental and the measured definitions locked in, an experiment is just a vague idea.
Okay, so we know we have to measure our dependent variables with extreme precision,
Yeah.
but memory and happiness are tricky to put a number on. How do we actually do that measuring?
Well, there are 4 distinct scales of measurement.
And you can think of them like rungs on a ladder. As we move up this ladder from the first scale to the fourth, we get progressively more precise mathematical information. Let's start at the bottom rung, the nominal scale.
The nominal scale is the most basic level. It simply assigns items to 2 or more distinct categories that can be named using a shared feature. But crucially, it does not measure their magnitude.
Think about sorting canines into friendly and shy categories. You are just grouping things by a label. You know they are in different categories, but you have no idea how much friendlier one dog is than another. There's no math involved, just sorting.
Exactly. Now, moving one step up the ladder, we have the ordinal scale. This scale does measure the magnitude of the dependent variable, and it does so using ranks. However, it still does not assign precise values.
So like a race.
Yes, think about a runner's place in a marathon. If you know someone came in first and someone else came in second, you can make a definitive statement about their relative speed. You know the first person was faster.
But you do not know their precise speed. The first place runner could have beaten the second place runner by 1 single second or by an entire hour.
Exactly.
And this is such an important thing for you to watch out for when you're reading the news. If an article claims a new drug is ranked #1 in clinical trials, you have to remember that ordinal ranks hide the actual distance between outcomes. #1 could mean it's twice as effective as #2, or it could mean it's only a fraction of a percent better.
That is a brilliant point. Ranks tell you the order, but they obscure the gaps. So stepping up again, we get to the interval scale. An interval scale measures magnitude using equal intervals between values. The distance between points on the scale is consistent.
The classic example here is measuring temperature in degrees Celsius. The difference between 10 degrees and 20 degrees is the exact same amount of heat as the difference between 30 degrees and 40 degrees.
Or Sarnoff and Zimbardo's 1961 0 to 100 scale. The intervals are uniform.
But wait, there's a catch with the interval scale. Right. It has no absolute 0 point. So if I'm using an interval scale like Celsius and the thermometer hits 0, that's just an arbitrary line we drew in the sand. It doesn't mean temperature stopped existing.
That is the crucial limitation of an interval scale. 0 degrees Celsius doesn't mean the total absence of heat, it's just another point on the scale. Which brings us to the top rung, the gold standard of measurement, the ratio scale.
Okay.
A ratio scale measures magnitude using equal intervals between values, just like the interval scale, but it also has an absolute true 0 point.
So the 0 actually means 0. The total complete absence of the thing you were measuring.
Precisely. Think about distance in meters or time in seconds. 0 meters means no distance whatsoever. 0 seconds means no time has passed. And because of that absolute 0, we gain a massive analytical advantage. We can finally make proportional statements.
Right.
With a ratio scale, we can confidently state that 2 meters is exactly twice as long as 1 meter.
Which you can't do with temperature. You cannot say that 40 degrees Celsius is twice as hot as 20 degrees Celsius because the 0 isn't absolute.
Exactly.
But with ratio scales, that kind of powerful mathematical comparison is fully unlocked. All right, so we've got our variables defined, we've carefully avoided confounding our experiment, and we've picked our measurement scale. But how do we know we can actually trust the data we are collecting?
That brings us to 2 massive pillars of scientific research: reliability and validity.
Let's tackle reliability first.
Yeah.
In the simplest terms, reliability is all about consistency.
Right. It refers to the consistency of your experimental operational definitions and your measured operational definitions. Think about a reliable bathroom scale. It should display the exact same weight if you step on it 3 times in the same minute.
Yeah, if it gives you 3 wildly different numbers, it's not reliable.
And researchers evaluate this consistency in 3 specific ways. The first is inter-rater reliability.
This is the degree to which different observers agree in their measurement of a behavior. So if you have 3 different observers score the same set of personal essays for optimism, and all 3 observers give similar scores, your inter-rater reliability is high.
But if their schools are all over the map, your measurement procedure is too subjective and inconsistent. The second way is test-retest reliability. This looks at whether a person's scores are consistent across 2 or more administrations of a measurement procedure.
Right, like if you take a test today and take it again later, do you get a similar result?
Exactly. For instance, administering the Wechsler Adult Intelligence Scale revised boys are twice 2 weeks apart. If the scores from the first test are highly correlated with the scores from the test has high test-retest reliability.
And the third type is inter-item reliability. This measures the degree to which different parts of a single instrument, like different sections of a long questionnaire, achieve consistent results.
Right.
If a personality test has 10 questions, all designed to measure extroversion, a person should be answering those 10 questions in a consistent pattern. If they answer 5 of them like an introvert and 5 like an extrovert, the items aren't reliably measuring the same thing.
Okay, so reliability ensures your measurements are consistent. But consistency isn't enough on its own. You could have a bathroom scale that consistently tells you that you weigh exactly 10 pounds. It's incredibly reliable, but it's completely wrong.
That's where validity comes in. Validity means accuracy. It means that your operational definition actually manipulates the independent variable or measures the dependent variable that it claims to. And just like reliability, there are different flavors of validity.
Starting with the most basic face validity. This is the degree to which the validity of a manipulation or measurement technique is self-evident. It just looks right on its face.
Like using a ruler to measure pupil size has high face validity, because obviously a ruler measures length.
But it's considered the least stringent form of validity, because licks can be deceiving. So we move to content validity. This is about how accurately a measurement procedure samples the content of the dependent variable. Are you testing what you actually taught?
Oh, this is the ultimate nightmare scenario for any student. An exam that is supposed to cover chapters 1 through 4 of a textbook. But when you sit down, it only contains questions about chapter 2.
It's the worst.
I would be furious. That exam has incredibly poor content validity because it didn't sample the full domain of what it claimed to measure.
Next up is predictive validity. This looks at how accurately a measurement procedure predicts future performance. The standard example here is the ACT.
Right. The ACT only has predictive validity if the scores students get on it are significantly correlated with their future college GPAs. If high ACT scores don't actually predict high college GPAs, then the test lacks predictive validity. It's not doing what it claims to do.
And finally, we have construct validity. This is how accurately an operational definition represents a broader, abstract theoretical construct. Think about studying abusive parents.
That's a really complex, multi-layered psychological concept. You can't just measure one simple thing.
Exactly. A construct of abusive parents might need to include multiple measurements, such as how they perceive their neighbors as unfriendly. It's about ensuring your specific, observable measurements truly capture the complex idea you're aiming for.
But if we connect all of this to the bigger picture, while all those types of validity are important, there is one specific type that is the holy grail of experimentation.
Internal validity.
Yes. Internal validity is the degree to which changes in the dependent variable across treatment conditions were strictly due to the independent variable. High internal validity is what allows you to establish a true cause and effect relationship. It proves that your manipulation and absolutely nothing else caused the change.
And this is the constant battle in science.
Here's where it gets really interesting. Because achieving that high internal validity is like trying to protect a fortress from invaders. There is an entire rogues gallery of threats to internal validity.
These are the enemies of truth in an experiment, mostly driven by the problem of confounding we talked about earlier.
Right. If we go back to the idea of a study comparing the effects of meditation and prayer on blood pressure, the whole thing is totally confounded if one of those groups happens to exercise more than the other. You wouldn't know if the blood pressure changed because of the meditation or the exercise.
So let's play detective. There are 8 specific threats that researchers have to constantly guard against.
Walk us through them.
Gladly. Threat number 1 is the history threat. This occurs when an event outside the experiment threatens internal validity by changing the dependent variable. Imagine you are doing a study that involves weighing subjects. Subjects in Group A were weighed before lunch, while those in Group B were weighed after lunch.
Wait, so the outside event eating lunch changes the outcome entirely? Lunch literally ruins the data.
It really does.
That's amazing. You meticulously plan a scientific study, and a turkey sandwich destroys your life's work. Yeah. Okay, what's threat number 2?
Number 2 is the maturation threat. This happens when physical or psychological changes in the subjects themselves threaten internal validity by changing the dependent variable over time. Think about boredom.
Uh,
If you have subjects doing a long, tedious proofreading task, their boredom is naturally going to increase over time, causing them to make more errors. The increase in errors isn't because you're independent variable, it's simply because they got bored as the clock ticked on.
they matured or deteriorated during the study. Makes sense. Threat number 3 is the testing threat. This one is fascinating. It occurs when prior exposure to a measurement procedure actually hacks performance on that measure during the experiment.
Yes, think about measuring blood pressure. Imagine your experimental subjects used a blood pressure cuff every single day of the study, while the control subjects only used it once during a pretest. Over time, the experimental group gets comfortable with the procedure. Maybe their heart rate lowers simply because they are no longer anxious about the machine.
The prior testing itself changed the outcome. They just got used to the equipment. Which actually brings us to threat 4, the instrumentation threat. This is when changes in the measurement instrument or the measuring procedure itself threaten internal validity. It's essentially equipment decay or observer fatigue.
Exactly. Imagine reaction time measurements becoming less accurate during the experimental conditions than the control conditions. Maybe the battery in a stopwatch is dying and it's lagging. Or, more likely, the human being clicking the button is getting tired after 3 hours, and their own reaction time is slowing down.
That is so subtle, but so incredibly destructive to the data. Okay, number 5 sounds a bit intimidating. The statistical regression threat.
It sounds complex, but let's break it down simply. This threat occurs under a specific set of circumstances. When subjects are assigned to conditions on the basis of extreme scores, the measurement procedure is not completely reliable, and then the subjects are retested using the same procedure to measure change.
Let's use an analogy here. If you happen to take a math test on the absolute best day of your life, you slept great, you guessed lucky, and you score incredibly high, the odds are that the next time you take it, you'll score closer to your normal average. You regressed back to the mean.
Right.
It wasn't the experiment that changed your math skills. It was just the mathematical probability of returning to average after an extreme fluke.
That is a perfect way to look at it. If researchers pick people who scored unusually high or unusually low on a wonky test, their next score is mathematically likely to move back toward the average, regardless of what the researcher does to them. Now, threat 6 is the selection threat.
This happens when individual differences are not balanced across your treatment conditions by your assignment procedure. So even if you try your best to randomly assign people to groups, you might accidentally end up with subjects in the experimental group who are simply more extroverted than those in the control group. Just bad luck of the draw. But if extroversion affects your outcome, your study is confounded from the very start.
Which brings us to threat 7, which has a rather grim name-subject mortality threat. In this context, mortality usually just means dropping out of the study. This threat occurs when subjects drop out of experimental conditions at different rates.
And this is something you should absolutely watch for when you are reading headlines. If you are reading an article about a new miracle diet, but half the people in the experimental group quit because the diet was too hard to follow. Wait, the glowing results you're reading only apply to the ultra-disciplined people who actually stayed.
Exactly right.
That's subject mortality in action. Even if the groups started out perfectly matched, that differential dropout rate produces artificial differences in the final data.
And finally, threat number 8, selection interactions. This is essentially a team-up of threats. A selection interaction occurs when the selection threat we just talked about combines forces with at least one other threat, like history, maturation, statistical regression, subject mortality, or testing.
So not only did you accidentally get a group of highly extroverted people in your experimental group, but because they are extroverted, they react differently to an outside event or they get bored faster. It's a compounding disaster for internal validity.
It really is a minefield. So, given all these subtle ways things can go wrong, how do scientists prove to the rest of the world that they actually did things right? That brings us to the methods section of an APA research report. This is the blueprint. It is how scientists communicate all of this careful, meticulous planning.
And the primary goal of this section is replication. The method section must provide the reader with sufficient detail, the exact who, what, when, and how to perfectly replicate the study. If someone else cannot follow your method section like a recipe in a cookbook and conduct the exact same experiment, you haven't written it correctly.
The core components you must describe are the participants, the apparatus or materials, and the procedure. And there's an interesting clarification about the apparatus section. You don't always need a dedicated section just to list everyday items. An apparatus section is only appropriate when the equipment used was unique or specialized.
Right, you don't need to waste time describing a standard yellow pencil. But if you used a highly modified computer keyboard that tracks keystroke pressure, you need to detail exactly what it does and its specific capabilities.
Exactly.
Why? So that the reader can better evaluate your findings or go out and build their own to see if your findings hold up. Because without the ability to replicate it, it isn't science. It's just a personal anecdote.
It's all about transparency.
So what does this all mean? When we zoom out, what we've seen today is that creating a valid experiment isn't just about throwing some people in a room, manipulating a variable, and writing down what happens. It is a highly structured, incredibly rigorous defense against human error, wonky measurement scales, varying dropout rates, and even the exact time someone ate their lunch.
It really is.
It's an entire system designed to strip away the noise so we can actually hear the signal. It's given me a whole new appreciation for the phrase "studies show." I'll hand it over to you for a final thought.
This raises an important question, something really profound to think about as you go about your day and encounter new data. If every single experiment is potentially vulnerable to such subtle, almost invisible threats to internal validity, from how bored a single participant happens to be to exactly when they ate their lunch, is a perfectly flawless experiment ever truly possible in the real world? Or is the scientific method simply our best ongoing attempt to slowly, painstakingly narrow down human uncertainty?
That is a brilliant question to end on. Thank you so much for joining us on this deep dive. Keep asking questions, keep looking at the scaffolding behind the headlines, and keep evaluating the data you encounter in your daily life. Until next time, keep learning.